Okay, question 7. So we've got an exercise device called the chest expander, and this one is about springs. So this one is going to be about stretching and compressing springs. Complete the following sentences. When the springs are stretched, something energy is stored in the springs. So that's paper 1 content, and we're looking for the words elastic potential. Okay, figure 2 shows how the extension of the spring from the chest expander depends on the force acting on the spring. So if we look at this graph, we can see that it's going through the origin and it is a straight line. So we know that this is a directly proportional relationship. So how can we tell from figure 2 that the limit of proportionality of the spring has not been exceeded? So this experiment is one that we should have done, which is the Huxler experiment. And when you do Huxler, what you do is you plot the force and the extension. And you see that as you increase the force, the extension is directly proportional till a certain point, and we call this the limit of proportionality. And after that limit of proportionality, your graph will do something like that. And what's happening here is in this area where we've got our directly proportional line, we say that the object, in this case the spring, is behaving elastically. Because what that means is that when we apply a force to something that is elastic, we deform it, we either stretch it or compress it. But as soon as we take those forces away, then what will happen is that the spring or the object will return to its original shape. If we apply a force that is too big, so if we squash it too much or we stretch it too far, then we hit something called the limit of proportionality. And after this point, the object will not return to its original shape. So we say that it's inelastic. So if we talk about this, how can you tell from figure 2 that the limit of proportionality has not been exceeded? It's because this is a directly proportional line. So it's because the line is straight. So it's a straight line of best fit, directly proportional. So what we're looking for is it to stop being directly proportional. Use the data in figure 2 to calculate the spring constant of the spring. Give the units. So spring constant. We're going to go to our physics data sheet. We are going to look for a formula that has the spring constant in it. And if we're using the graph, we've got extension and force. So we can pull up values at any point for extension and force. So what we'll try and do is we'll just try and pick an area on this graph where the numbers are dead easy, such as 160 and 0.40, which I've slightly missed. All right, probably hard to see. I'm going to use this pink colour because it's more vivid. I'll use a thicker line, so you can see there. All right, so that 160, and that lines up with that 0.40. So when extension is 0.40 meters, the force is 160 newtons. So we can use those two values. So let's do that. So extension equals 0.40 meters, and when it's extended by that much, the force applied is 160 newtons, and we are trying to find the spring constant. So we want to find a formula with spring constant, extension, and force in it. Let's go to the data sheet. Let's get rid of the one we previously did. So we're looking for spring constant. Okay, let's have a highlighter that isn't a dirty brown colour. There we go. All right, so look, spring constant. Spring constant. I'm not seeing it. Let's try over here. Aha! Look, spring constant. Bigger highlighter. Force equals spring constant times by extension. F equals KE. Force, spring constant, times by extension. F equals K times E. So, use our formula. So, FIFA, the force is equal to spring constant K times by the extension. Force should be in newtons. Spring constant don't worry about that, when the extension should be in meters. Very often on these graphs you see the extension in centimeters. This one is in meters, so that saves us a job, but otherwise we would have to convert it to meters. So let's input our data. So the force, we said when the force is 160, the spring constant we don't know, but the extension is 0.40 meters. So we have to fine tune this by rearranging it so that K is the subject. So K is currently being multiplied by 0.40. So we're going to divide by 0.40 times and divide by the same thing would equal 1. Therefore that cancels out, just leave K. If we do it to one side of the equal sign, we've got to do it to this, so divide by 0.40, and that leaves us with 160 divided by 0.40 is equal to the spring constant. So let's do that. So clear that up. 160 divided by 0.40 gives us 400. All right, we'll check that again. 160 over this time, 0.40. 0.40 gives us 400. So it will be 400. And it wants the unit. So in order to figure out the unit, we just look at what we've done. So we took the force and we divided it by the distance. So we had, this force was in newtons, and we divided that by meters. So it's going to be Newton / meters. Capital N, lowercase m. 3 identical resistors joined in parallel in an electrical circuit share the total current in a circuit. In a similar way, the 3 springs in the chest extender share the total force exerted. By considering the similarity, use figure 2 to determine the total force exerted by the chest expander when each spring is stretched by 0.25 meters. All right, and then we have to work out the force. So what we have to do is we have to figure out the we're looking for a total force. So we have to figure out the force of one spring and multiply it by 4, because there's 4 springs. So 0.25 meters. So if we go to our graph, I'll get this pink pen again so it's a little bit more obvious. 0.25 meters, draw a line, hit the line that's fit, draw a line down, and we have got 100, a force of 100 newtons. Okay, so we have got, so one spring at 0.25 meters requires 100 newtons of force. The question, though, said that we had 3 springs. So we just do 100 times by 3 is going to give us 300 newtons of total force required. 300 newtons. Okay, this question here. Now, I've seen this question pop up multiple times on multiple different papers, and the first time I saw it, it was worth 5 marks, and now it's worth 3 marks. It's a strange one because I think this is a 5-mark question. This is a really tricky question. This one it requires a linked formula, but it's a really nice question. It's one of those questions that separates. It's a good, what I always think of as a separator. All right, a lot of people can do using formula. A lot of people can rearrange formula. But the thing that separates the higher grades are, can people link formula together? And this is a chance to do that. So when you see these papers, these questions come up, if you're confident with linking formula, you should think, great, this is a chance for me to separate myself here and show that I'm working at a higher level. So let's work out what we've got. So we have got a height, because it says it is moving vertically upwards. So that would be, a height. So we've got a height. Could also be a distance, I suppose. We've got a mass of 65 kilos. So I'll label that as the mass. And it said the student is able to do 12 chin-ups in 60 seconds. So we've got a time. And we've also got the fact that he's doing 12. So like with the chest expander, the idea, we're not just working out one. We've got 12 pull-ups. So if we calculate the power of the student, he's not just doing one, he's doing 12 pull-ups. All right, so it wants us to find the power. And we're told that gravitational field strength is 10. Now, whenever you see gravitational field strength in there, you should probably be thinking, oh, I'm going to be using that formula, EP equals mass times gravity times height, and you would be probably right in this case. But let's go through it. So what we would always try and do when we're using any link equation is, again, use FIFA, always have that structure that you follow, because it means that you won't try and second guess yourself and you won't try and do anything different. You'll just follow your structure and it'll lead to a logical outcome. So we're going to put in a formula. Initially, we're trying to find power. So we've got power, we've got a time, we've got height, we've got mass, and we've got gravitational field strength. So let's go to our data sheet and let's see what formulas have got power in it that have got some or all of those things in it too. Now there are quite a few power formulas, so they're all over here, look. So we've got power equals potential difference times current. And that's not going to be the one because that was to do with electricity. Power, current times resistance, again, electricity. Power equals, energy transferred equals power times time. Now that is to do with electricity, but that would work. But actually, it's not the best one because we're trying to find power. So if we can have power as the subject, that would be even better. But that one will work because we can get an energy transferred and we've got a time. So I'll leave it like that for now. But there's actually a rearrangement of that here. Power equals energy transfer divided by time. It's the same formula, it's just put on the data sheet twice because this bottom one is normally for electricity and this top one is normally for anything to do with movement and forces. And energy transfers. Power equals work done divided by time. That would have worked as well because work done is just an energy transfer. So those formulas mean the same thing. But we'll take just that top one. So power is energy transferred divided by time. So let's use that. So power equals the energy transferred divided by the time. Now, let's plug in what we've got. We're trying to find power, so we don't have that. We don't currently have an energy transferred, but we do have a time, which is 60 seconds. So why have I chosen that formula? Well, because I know the fact that it mentioned gravity, I know there's a way to get energy. So what we need to do when we do this is we need to use another subject, another formula to find the other missing value. Because in a formula, the only way we can solve it is if we only have one unknown. In this case, we've got two unknowns. And the thing we're trying to find is power. So that we're not going to be able to get that anyway in this first instance. So the thing that we should be able to find is energy. So we have to find another way of doing it. So let's find a formula that allows us to get energy. Now, I've hinted at it. It's the one that's got gravitational field strength. We've got a height. We've got a mass. Let's go to our data sheet. Really common equation, this one. All right, I'll get the highlighter again. Gravitational potential energy is mass times gravitational field strength times height. That's what we're going to use. EPmg. So let's use that formula. EP equals mass times gravitational field strength times by our height. So input our values. We don't know energy. Now it's EP, it doesn't matter that it's any potential. Energy is energy. So remember conservation of energy. The idea that in a closed system, the energy before is equal to the energy after, just like the idea of conservation of momentum. Before is equal to after. And conservation of mass in chemistry. It's always the same idea. So it doesn't matter that it's energy potential because it's energy. So mass 65. Gravitational field strength, we're told to use 10. So if you use 9.8 there, you will be penalised because it says use 10. And the height is 0.40 metres. So, it could have given you that in centimetres, it could have asked you to convert, but this question is hard enough to do anyway rather than starting doing that. So we do not need to fine tune it. We can just straight away go and get an answer here. So we don't need the fine tune part of the FIFA. So 65 times 10 times 0.40. So let's grab, oh, currently I'm struggling. There we go. So 65 times 10 times 0.40. Just checking that I've used everything correctly. Yep. So that gives us 260 joules. So answer is 260 joules is the energy. So we are going to use that in our original formula. So we go back to our formula. We're now going to fine tune it by writing power equals 260 divided by 60. So that is the power that the student is transferring in a minute. Sort of. I'll explain why in a second. Yeah, we can do it this way. I've just realised in my head as I'm doing this, because the power is all about the energy transfer, but in a minute he's doing 12 chin-ups, and we've only calculated the height of one movement. So actually what we need to do is we need that energy should be 12 times that energy. Okay, so we can do it a couple of ways. We can do this and then times it by 12, or we can do the energy times it by 12. Let's do it this way and times it by 12. So in order to get the power, we do 260 divided by 60. So let's do that. And we get 4.33 recurring. So the power is equal to 4.333. But that's for one pull-up. Remember, he's doing 12 pull-ups. So we just do that. So 4.333 times by 12. Now for this one, rather than writing 4.333, because we've simplified that a little bit, we've rounded it down, it'd be better if we just use the answer. So if we just go equals and then press answer times by 12, that gives us 52. So the power for 12 pull-ups is 52 watts. Okay.